Now, I want to give you a brief overview over the agenda. First, I want to give a short introduction in the analysis of pesticides. Then I will show you a method for 300 plus pesticides which has been validated according to European regulation. Then I will explain shortly what triggered MRM is, and later on I will show the qual workflow using the triggered MRM and some real-world examples. And afterwards there will be a short summary conclusion. Let's go to the topic. So pesticide residues in food and feed are something which is normal because there is no way of producing food without the use of pesticides. So you do have some pesticide residues, and that is not necessarily illegal. There are tolerable concentrations, and those are typically regulated by law. In Europe, that's the European Regulation 396, 2005, and in America, it's the American Federal Regulation 40 CFR Part 180. Both of these regulations are very similar, and they give tolerable concentrations in different food commodities. So just as an example, in this European regulation, we have more than 170,000 matrix pesticide combinations for which MRLs, so maximum residual limits, have been specified and which need to be tested in the different food products. So the challenge here is to analyze the large variety of different matrices, and you also have the challenge that the pesticides have different chemical properties which require a method which is universal for polar and less polar compounds, and which is able to detect different groups of compounds. What is of benefit is that there is a generic extraction, the so-called catches extraction, which is these days the most common and the most established extraction method for pesticides in food matrices. And because it is such a generic and universal extraction, you typically have a very high matrix concentration also in the final extract, which requires later on a separation based on gas chromatography or liquid chromatography and coupled to a mass spectrometry, which gives you the necessary sensitivity and selectivity. In Europe, pesticide methods need to be fit for purpose, and that means that they are validated according to the European guideline Sanco 1249/5 of 2011. So this is also the frame of what we did in the experiments later on. And so there is, of course, the questions which compounds to analyze, and there is a ranking of pesticides which is published by the European Reference Lab for Pesticides, and it includes more than 1,100 compounds, and that are pesticides which are currently used or which have been used, and also some metabolites of importance. And the ranking of these pesticides in this list is based on toxicological data, the residue situation, so how often has it been found in food products, and also on the agricultural usage. So a compound which makes it high in this ranking is probably very toxic. It is commonly used, and it's often found in food products. In a recent conference, I heard that in Europe there are about 600 compounds included in the routine monitoring programs, but only 150 of these pesticides are often found in food commodities. And I expect that this is the same also for the US. Now, we do have a portfolio of triple quad instruments which allow you to run this analysis with LC MS. And all of these instruments are capable to do the job. So we have the 6420 triple quad, which is a robust, easy to use instrument with a very low cost of ownership. But it is possible to run the analysis with that instrument. If you want to include also negative compounds in the test suite and do a fast polarity switching, you have to go for the 6430, and then by using the Agilent Jetstream instrument or ionization source on the instruments, you get more sensitivity and you can do fast polarity switching, which then of course allows you to analyze more compounds and get lower concentrations. Today I want to focus on our most advanced instrument and most sensitive instrument. It's a 6490 triple quad instrument. It makes use of the Agilent Jetstream ionization, and in addition it has an eye funnel, curved hexagonal collision cell, and this gives you the most sensitivity you can have today, and it also allows you to do a fast polarity switching, and it's perfect for the most demanding application. And without any question, pesticide screening and confirmation is one of the most demanding applications on the planet. Now, the question is, why do I want to use such a sensitive instrument if the others do the job as well? And the answer is, well, you probably want to increase the number of analytes in the method, and you want to analyze them with a single injection, even compounds which might have a lower abundancy. You want to go to lower LOQs for pesticides in the complex matrices. You want to extend your analytical scope to the analysis of baby food, which also requires lower LOQs. And last but not least, it is a way to minimize matrix effects by diluting your, and then of course you also need to have a better sensitivity to detect the compounds even in the dilution. It is not only the triple quad which enables you to make these very sensitive analyses. It's also the combination of the 1290 UHPLC system I used and the dynamic MRM software, and then of course, as I mentioned earlier, the Jetstream source and the dual ion funnel to give you that utmost sensitivity you need for that. Now, just I mentioned it already, but just to give you a very quick overview about the technology, the 6490 has an improved ionization and ion transfer technology. So we do have the Agilent Jetstream, and then we have a hexabore capillary to get more ions into the system. And if you get more ions and more gas, which is rich in ions, into the system, you have to get rid of the gas again. So for that purpose, we have a dual ion funnel approach. And then we do have a curved collision cell, which helps you to get rid of neutral noise. And as you all know, sensitivity is signal versus noise. So getting a lower noise count is a better sensitivity, and then we have improved quad drive electronics, which can enable you also to run with higher resolution on the quadrupole. A quick overview about the ion transmission. So we have the hexabore capillary, which samples a lot of the gas, which is rich in ions from the ionization source, and then we transfer the ions via the two ion funnels into the system, while at the same time the gas is pumped away. And if you look very carefully, you can see that the first funnel is slightly moved out of the axis, so that the ion need to follow a curved way. And this is again a way to eliminate neutrals and to get the ions focused into the system. Okay, what I now want to show you as a first part of this presentation is a method which has been set up for more than 300 pesticides. A very quick method with a 13-minute runtime and 2 minutes of equilibration. It's injecting 2 microliter of the catcher's extract, and this method has been validated for different food commodities, and I want to briefly show you the results of the validation study. So a 1290 Infinity system has been used. 100 millimeter fully end-capped Thorbuck's Eclipse Plus column has been used, and ammonium formate and methanol was used as the mobile phases. We do have a very steep gradient in the beginning to 50%, and later on a very shallow gradient, so that we get a better separation where the majority of pesticides elutes. The triple quad instrument was the 6490 instrument. It was operated in the dynamic MRM mode with a cycle time of 600 milliseconds. The total number of MRMs was 635, and that allowed a minimum dwell time of about 5 milliseconds, whereas we had a maximum dwell time, especially in the beginning and at the end of the run, of nearly 300 milliseconds per transition. I don't expect you to read all these compounds, but that is a list of compounds which has been analyzed in that method. In total, you can see 313 compounds, and in addition 9 isomers. And this is a shot of a result. So you can see a very crowded chromatogram. Most of the compounds, or all of the compounds, elute within the first 11 minutes. That is a spiked tomato sample, spiked to 10 micrograms per kilogram and then extracted. What you can see here in the most crowded region of the chromatogram, around 7.5 to 8.5 minutes, we have about 160 MRM transitions in less than 1 minute. So very crowded, very busy, and this method has been validated now for different matrices. This is just to give you an idea about the result of the tomato. So we analyzed the 313 compounds, and if you go down to the MRL of 10 micrograms per kilogram for most of the compounds in Europe, you can see that you still see all of the compounds. If you go further down to 1, which is 10 times below the MRL, you still see much more than 300 pesticides, and even if you go 100 times below the MRL, you still can validate 280 compounds in that method. So that is a quite promising result, because the list of compounds has not selected because of the best performing compounds. It has been selected based on the on a higher ranking in the Check Your Scope listing, which also included some compounds which are not really nice to be analyzed on the triple quad. And if you look, for example, to this compound, all of those of you who analyze pesticides know that ivermectin is a difficult compound. And if you look at that, this is a 0.5 microgram per kilogram concentration in the tomato extract, and you still see a very nice peak for the ivermectin B1A with a signal to noise well above 10. And if you look for the ivermectin B1B, which is even a little worse than that, you can still see that this is very nicely with signal to noise well above 10. And so also for the very difficult compounds, you can see a very good sensitivity of the system. And so the validation has been done not only on tomato, which is a relatively easy matrix, but also on rocket and black tea, which are very difficult. Then on acidic compound food product like lemons, we have a matrix which is rich in starch, which is the wheat flour, and then we have the sweet pepper, tomato, and cucumber, which are the more easy matrices. And if you now look at that, you can see that even in the complex matrices, 100 times below the MRL, you can validate for most of the matrices about 300 compounds, and for all of the matrices above 250. Now let's go to one of the more difficult matrices, and that is the black tea. And you now see that in detail. So 4 times below the MRL, you still have about 300 compounds which can be validated according to the Sanko regulation. And a few examples here. So oxamyl and carbendazim are quite high. Check your scope listing, and you can see at 0.5 micrograms per kilogram in the black tea extract. You can see them very, very nicely, well above the LOQ. And again, if we have a look at the avamectin at 2.5 micrograms per kilogram, about the same as we have seen before. So the question now is, and I mentioned that earlier, that in that difficult matrices, a dilution approach is very often very nice, because it does reduce matrix effects, and that has been tested for all the compounds. So you can see here now an example for the dilution of a black tea extract, and that is a compound which is called monocrotophos. And if you now take a 5 microgram per kilogram sample and do a 1:2 dilution, and you can see that the signal does not drop by a factor of 2. It's nearly constant, and even at a 1:5 dilution, it is nearly at the same height. And only then the intensity goes further down, but we have still a very good signal-to-noise ratio for a 1:50 dilution, which is corresponding to 4 femtograms on color. Now, if we go to another compound like fubaridazole, you can see that for a 1:2 dilution, you even see an increased signal. So that means that by doing that dilution with acetonitrile, you do dilute the matrix more, and therefore you free up spaces at the surface of the charged droplets, which allow your compounds to be ionized. And this is why the signal for your target compounds increases sometimes, while the matrix is reduced. Now let's dive a little bit deeper into the results, and let's start with the fubaridazole. So what you can see here now on the left-hand side is the screenshot of the quantitative software with at a concentration of 0.1 picogram per microliter, corresponding to 0.1 microgram per kilogram. We have a very nice calibration. You can see the two traces, and if you look at that with a 600 millisecond cycle time, we have 27 data points across the peak. If we now have a look on the different matrices, and now the next slides are always the same, so you can see on the first picture you have the solvent, then you have the black tea, cucumber, lemon, pepper, rocket, tomato, and wheat flour matrix, and the signal is locked. So you would expect to have any matrix effects, that you get the same signal as for the solvent standard. And if you look at that, you can see that for the black tea, the signal is much lower than you would expect. You have some suppression probably for the lemon, and for some others you might even have an improvement or an increase in the signal, or you might have a background contamination, because all of them have, of course, been spiked with a pesticide standard. And if you look at that, the expected concentration is 1 ppb here. And so for the black tea, we just have 1/4, 25% recovery. The rest is well above the 70% which is required to be validated in the method. If we now do the dilution experiment, and you can see that for the fubaridazole, of course you would expect that the signal, that the concentration here is 1 ppb, then here it should be 0.5 ppb, 0.25, and so on. So for the dilution steps, you would expect a decreasing concentration. And if you compare now the measured concentration with the expected, you can see that the recovery increased. And starting from a dilution of 1 in 5, you are actually within the 70 to 120% recovery, which is required for a successful validation of the pesticides compared to a solvent standard. So that shows you a dilution actually helps you your compound into the validation in the range where you can validate your method again. Now the question, is that true only for the fubaridazole? And I just show a few other examples. As I said, methomyl and oxamyl are relatively high. Check your scope listing. So therefore I selected those two. Again, a 0.1 ppb sample, relatively good signal, a nice calibration. And if you look at that, you can see again the same for the black tea. We do have about 50 or just 40% of the signal, and for the rocket, it is nearly disappeared. So we just have about 2% of the signal back. Now, what happens if I do the dilution here? First for the tea, again, same behavior. The signal does not drop as much as it is expected if you do the dilution. After a 1 in 5 dilution, you are back at 70% recovery, so successful validation is possible. And if you now look at the rocket sample, you can see in the non-diluted sample, you cannot even see it. And if you do a 1 in 2 dilution, you're already back to where you expect the signal to be. So therefore, in the rocket sample, it was quite important to do a validation, a dilution before the injection. Otherwise, you probably would have missed the compound. And that was a very interesting result. And this is not only based on one injection. We actually did 5 replicates and also 5 different dilutions. So this has been shown to be consistent with replicate injections. Now, is it consistent with other compounds as well? And so the question was, how does oxamyl behave? Because it's a similar compound, and if you get that, you can see a very, very similar behavior. Again, in the black tea, you have about 40% recovery only, so you would expect by diluting it, it would come back up again. And if you look here for the rocket sample, you can see here at the very beginning, you can see this is the compound signal, but it is overlaid by a huge matrix peak, which is giving you a signal on the major transition, on the quantifier transition, and therefore this is not really the true value, because it takes into account that this matrix interference. And what happens now if I do the dilution of the rocket sample? And now you can see this is a non-diluted sample, and if I do a dilution, the signal for the oxamyl goes up, and the signal for the matrix interference goes down, and there after a dilution of 1 in 5, the signal stays constant for both of these compounds. So again, with a 1 in 5 dilution, it was possible to validate that compound. Now the question is, what happens if I have matrix interferences which actually show up on these different traces and might mimic one of my pesticides? And in this case, we were lucky that we had a qualifier which was selective enough to show, oh no, this is not the right compound. But sometimes it might happen that you even have on your qualifier trace a signal which might mimic a pesticide. So how to deal with that? And this is where the triggered MRM comes into the game. So what is triggered MRM? So if you think about the forensic science, you know that fingerprints are often used to identify a suspect. So and there are two approaches if you want to do that. One is you take the full fingerprint and you scan it. But as you can see, such a fingerprint is very, very difficult, and it might be more effective to take a few points within the fingerprint which are characteristic for that individual to do a database search and to find out if this is the suspect or not. And triggered MRM does exactly the same. So whereas you can compare a full scan product ion scan with a full fingerprinting, which requires a lot of information, which is not necessary because you would compare only a few signals of your targeted mass spectrum, the triggered MRM focuses on those information which makes this pesticide or this target compound unique. And there are two potential scenarios. So one is that you want to make sure that the compound of interest, and you acquire a spectrum and you attach that spectrum to your analysis report, and you can prove, yes, the peak I found is the compound, and that is true because, for example, you have the quantifier to qualifier ratio and you have a spectrum with a spectral match score. And the other one would be to eliminate for potential false detects which are caused by the matrix interferences, very similar to what we have seen for the oxamyl in the example earlier. Now, how does the triggered MRM work? Let's assume this is a pesticide peak. It's about 5 seconds wide. We do not have matrix. And what the system would do is that it acquires data points with constant cycle times across the peak. And once this primary transition goes over a certain threshold, you would acquire additional confirmatory ions over the peak. Now, as I mentioned earlier, the cycle time stays constant. So you do get equidistant data points across the peak, and you get a very nice UHPLC compatible peak, which you can use for a reliable quantitation. At the same time, as I said, if you go over that given threshold, where you acquire only the two primary, while you acquire the two primary transitions here over the full retention time window, you would then acquire secondary or confirmatory ions only once you were over this threshold, and only for a given number of repeats. So you do have a complete chromatogram for those compounds, for those transitions, but what you have is that these individual signals which are acquired for these data points are then later on combined to a spectrum which is normalized and stored into a library, or can be compared to a spectrum which is in the library already. Now, So we think triggered MRM is the ideal analytical solution if you want to do a quantitative run with your triple quad instrument, because it has a fast cycle time for short run times. It is accurate in quantitation, and it is very sensitive. And at the same time, it is qualitative because you get a product ion spectrum, which is library searchable and helps you to confirm the compound of interest. And at the same time, it's cost effective because it allows for high throughput with a single instrument. Triggered MRM only makes sense if you have the information about a number of transitions for individual compounds. So what we offer in this case is a triggered MRM application kit, which includes a database, a method, standards, on-site training, and a column. And in case of the pesticides, for example, the test mix includes more than 250 compounds. The database has 500 compounds with at least 2 transitions, and the library includes 250 compounds, which are often acquired with more than 8 transitions, and some of them even 10 transitions per compound. The same is available for veterinary drugs and for forensics toxicology. And again, the veterinary drugs mix has about 200 compounds, the database more than 500 entries, and the library also more than 200 entries. And for the forensics, 100 compounds in the test mix and in the library, and for the database, we have more than 500 compounds. The database looks like that, and as you can see, here is, for example, acephate. We do have 8 transitions here. The precursor is always the same. We do have the different fragments. We have the fragmenter voltage, the collision energy is optimized, and then we have an additional column which is called the primary column. So these compounds are acquired over the full retention time range, and the triggering column is then triggering the additional confirmatory ions. There are some smart tools in the optimizer software. So if you click here on the set primaries and trigger, it automatically select based on major abundance the 2 major transitions, and it would set the most abundant signal as a trigger. You then can define, okay, I want to include all these transitions. I want to focus on the 2, 4, 5, 6 most abundant, whatever you like. So it's very customizable and very easy to use. The acquisition software then shows up like this. So you do have the compound name, the precursor ion, then you have the product ions, and as you specified in the optimizer while you imported transitions, you have the primary transitions and the trigger transition, and you also specify a threshold. And this threshold is a compound dependent one, which can be automatically set based on a reference sample. So for example, you acquire your low concentration standard and you specify, oh, I want to have 10% or 50% the response of that low concentrated standard as my triggering threshold. And as you can see, all the fragments can be measured with the ideal collision energies, and that allows to be very, very sensitive even for the lower abundant fragments. So what we did is that we took the method you have seen before. We took out 120 compounds and created a triggered MRM method for those. The method included 2 primary transitions per compound, and we had in addition up to 8 different confirmatory ions, and compare the quantitative aspects. We we compared the triggered MRM method, which had then up to 10 transitions per compound in total, with a conventional dynamic MRM method, which had only the 2 primary transition. And then there were some real samples analyzed with triggered MRM to show you the benefit. A method, again, very similar to what you have seen before, slightly longer, because we used a longer column, and we used positive electrospray or Agilent jet stream. This is a chromatogram, so compounds have been selected across the whole polarity range. We selected very abundant ones, but also we selected a few compounds which actually generated a very low signal. And again, this is a sample. It's a 10 nanogram per milliliter, which has been spiked in a lemon extract here. This is now a of the 2 primary transitions of napropamide in lemon extract. It's the 1 ppb spike, so 1 microgram per kilogram. And as I mentioned earlier, since triggered MRM is acquiring with equidistant data points across the chromatogram, the peak shape of the primary transitions is not compromised, even when in this range of the chromatogram additional confirmatory ions have been triggered. And in the range where the napropamide eluted, in total more than 80 different transitions have been acquired, and you see that the peak shape is very nice. And this is an unsmoothed chromatogram, by the way. What is also very important is that triggered MRM produces high-quality spectra even at a low concentration. So what you can see here on top is the spectrum for napropamide, which has been acquired for the 1 ppb spike with 3 microliters injected, so 3 picograms on column. And if you compare those with the spectrum which has been acquired at 10 ppb spike, so 30 picograms on column, or even 300 picograms on column, except for the overall abundance, the shape or the pattern of the spectrum is very, very comparative. So what allows us to acquire the very high quality spectra at the low concentration is first the acquisition with the ideal collision energies for each individual fragment, and then in addition the relatively high dwell time you have available if you go on an MRM base compared to a full product ion scan. The method was as sensitive as the normal dynamic MRM method. So what you can see here is 120 compounds, more than 100 could be quantified below 0.1 microgram per kilogram. For the lemon extract, a few less, of course, as you would expect for a matrix stand. But you can see that most of them, of the 120 compounds, could be quantified below the 0.25 micrograms per kilogram. What you see here are the 2 calibration lines which have been acquired for oxamyl with the dynamic MRM method, including the primary transitions, and the triggered MRM calibration, which included in addition up to 8 confirmatory ions for each individual compound. And what you can see is that the slope of the calibration curves is very, very similar. And that means the slope is the same, then the overall abundance of the signal is the same, and the sensitivity of the 2 methods is the same. And of course, oxamyl, it's a favorite because it's so high it's such an important compound. But if you do it for all the different compounds, included in the method, and you compare the calibration slopes acquired with triggered MRM and the calibration slopes acquired with dynamic MRM, you can see that they all follow a line which has a slope of 0.9987, so very, very close to the theoretical value of 1. So that means that these two methods have been very comparable, and that is an important factor because if you run real samples which are not necessarily positive for all the compounds, the dwell times in the triggered MRM method might be completely different from one to the next. And what you can see here is a kind of a best case scenario for the dynamic MRM, where there are only 2 transitions acquired, and a kind of worst case scenario where all the different MRMs have been acquired in the calibration standards. So if that works and you have the same calibration, then you can be sure that you do a very accurate quantitation also of your samples. And now let's go into a few real samples. What you can see here are the 2 primary transitions for tebufene pyrrate in a ginger extract, and retention time is 15 minutes. That's about what you expect. You have 2 signals, and okay, slightly out of the expected ratio. What would you say? Is that tebufene pyrrate? Let's have a look to the spectrum, and if we look at that, okay, it looks similar, but if you look a little bit closer, then you can see that there are 2 transitions which are much higher than you would expect them in the tebufene pyrrate, and there are 2 other fragments which are completely missing. So that tells you, oh, it's probably something different, or at least there's something different underneath. Now look at the library match score the software is giving you. It goes down to 56, which is a relative bad value if you compare that to the real tebufene pyrrate, which has just a very slightly longer retention time. And if you compare that now, you get a perfect match for the reference spectrum, which is below here, and the acquired spectrum here, and you get a library match score of 99.8. If you now let's go to another example. This is again the MRM traces for a pesticide which is called tebuterone, and now is that the compound? And because we had that exercise before, you probably say no, it's not the compound because the ratio here is not perfect, and you are right. You can see this is again a natural compound being normal in a chamomile extract, and if you compare the spectrum, you easily can see that you have the 157 and 116, which are much bigger than expected, and you have a few other transitions which are much smaller than you would expect them, and consequently you get a library match score of 68 out of 100. Again, if you compare that to the real tebuterone, then you can see for a perfect match you get a perfect library match score of 100. Both of these examples were in the press because commercial labs had misidentified a natural compound in those 2 matrices, and it had to be tested from a different lab, and of course you can imagine that can have a huge economic effect, and also it's the reputation of the lab which is going down. So within the validation study we did, we identified a few other examples. So for example, dichlorophos in lemon, tifensulfuron in green tea, and imazalil and terbutylas chamomile. They all had similar. For all of these compounds, we had natural compounds which were similar in the retention times and gave signals on both the quantifier and the qualifier trace. And as you can see, by using the library match score, we basically got a match score which was below 60. Just for a few compounds, we got a higher score, but still much lower than the target compounds. And since we have the concept of the outlier flagging in our compounds at a glance, which is our high-throughput view of the quantitative results, you can flag all the results which have a low library match score also as an outlier, and then you would get a red background color, which then allows you to navigate quickly to the compounds which either have a low library match score or are out of the limits for one of the other outliers you specified. And here is just the example we did before. So the t-butyrone in the chamomile extract, and you can see for the standards and also for the spiked chamomile extract, you could see the right peak has been marked. It has a high library match score, but for the chamomile extract, which was not spiked, although you can see a peak, you get immediately a flagging because the library match score was below a given threshold. With that, I'm at the end of my presentation, and I would like to summarize. So what you have seen is that the combination of the 1290 Infinity UHPLC with the 6490 triple quad allows short run times and large suites of pesticides in one injection. We have a validated method for more than 300 priority pesticides, even in challenging matrices. Dilution is a possible way to overcome matrix effects like ion suppression, and so it allows for a quantitation based on the solvent calibration. And with the dilution, you do not only improve the quantitation, but you also improve the robustness of your system because you inject less matrix. So an increasing number of analytes and challenging matrices also increase the probability of erroneous signals on the MRM traces of pesticides, potentially causing false detects. And for that, I wanted to show you the triggered MRM, which enables spectral confirmation even at the LOQ levels. The method gave you the same quantitative performance than traditional MRM methods. The new data and libraries are seamlessly integrated into the software, and the automatic library matching allows an efficient data review and automatic flagging of suspect cases. And as an outlook, I would say I expect that by using a only primary transition in MRM in the future, we might extend the scope of multi-residue methods to up to twice as many compounds, because you then only trigger the spectra if the compound has been detected on the primary MRM, and you get an identification or confirmation based on the spectra. With that, I would like to give you two application notes for your reference. The first one is already published. The second one will be published in a week or so. That will describe the validation a little bit more into detail. And I would like to thank you for your attention, and I would like to thank my co-workers for their help with that application. So thanks again, and I would hand over to Rita and ask if we have some questions already, and feel free to ask questions now.
And we would like to thank you, Dr. Gloner, for a very interesting and informative presentation. And before we go to our Q&A break, I'd like to ask our audience a few questions concerning the seminar and also for Agilent presentations. We hope you found this informative and useful, and we do value your opinions on how Agilent can better serve you. The poll is now open on the lower right-hand side of your console. We thank you for taking the time to answer these questions. And as you are reviewing the poll questions, I would like to remind you concerning the Q&A. You may ask questions by putting your questions in the Q&A box addressed to presenter host, or if you wish, you may ask questions over the phone line by pressing *1 on your touch-tone phone. The operator will open your line, and if your question has already been answered, or if you wish to remove yourself from the queue, please press the # key. All right, so that we do not have any delay for the questions that we already have, let me go ahead and ask the first one. If users have to generate their own TMRM library spectra, how automated is the TMRM production ion selection and other MRM parameters?
The TMRM is fully integrated into the optimizer software. So in the current version of the software, you are able to select a given number of transitions, and by giving optimizer either the precursor mass or the molecular formula, you can force optimizer to run the optimization and to create this database, which I have shown before, also for your target compounds. So you, for example, say you want to have 6 or 8 different fragment ions. They are optimized, they are stored in the database, and you then can upload them into the acquisition method later on. Once you acquired, for example, a reference standard, you also can use our software to create automatically a reference library based on the response your analysis gave for that individual standard or that compound, and that is done really in a few seconds. So it is fully automized, it is fully integrated into the optimizer workflow, and so it is a very nice and smooth workflow for you to use the software.
Thank you. Dr. Gloner, let's move on to the next question. Was the solubility or ion suppression the key for determination of the recovery?
That, of course, is always a difficult question, but in this case, because we used the same extract and we diluted the same extract with acetonitrile, so I do not expect that the solubility was the major reason for the lower signal. It is really think that by diluting the sample with acetonitrile, you later on have more capability to charge your target analytes in the electrospray process, and therefore do not lose so much of your target compound, and you get a better signal. So it's really a matter of the ion suppression, and there are some nice papers which have been published last year about this dilution approach, which show exactly the same behavior, probably on a few other examples.
Thank you. Before we go to our next question, let me check the phone queue. Latif, is there anyone waiting in the queue?
I show no questions in the phone queue at this time.
Thank you. Okay, Dr. Gloner, our next question. Is there a way to add a pesticide that is not in your library and database?
Yes, of course. That is the way I just described. You use Optimizer, which is our software, to to do the optimization of the MRM transitions and conditions, you run the individual standard, you acquire the transitions, you run the sample, and then you can update the database and libraries with that acquired spectrum. And yeah, that's as I explained it earlier. It's a very smooth and easy to follow workflow.
All right. And our next question: is it possible to acquire triggered MRM spectra for multiple peaks in the chromatogram?
Yes. The way triggered MRM works is that triggering is armed once you exceed a given threshold, and then you can acquire for a given number of repeats, and as soon as you reach that, and your signal of the primary transition goes back beyond the threshold you specified, the triggered MRM is rearmed, so that for any additional peak, it might be an isomer or it might be a matrix interference. It is rearmed and it will trigger again, so that you have the triggered MRM spectra available for all the peaks in your chromatogram. Yes, possible.
Thank you. And before we go on to any further questions, I'd like to make a few announcements to our audience. Following the seminar, you will be receiving an email with a link to the recording of this presentation. In addition, we'll provide a link to our library so you may download a PDF copy of the presentation. And we are getting close to running out of time here, but there is, let me ask this question. Why is the signal intensity not affected by the changing dwell times when additional concurring MRM transitions are measured?
That is a very good question, and the answer is that our systems average signal over the dwell time, and that means that even for long dwell times, you have a very constant signal, but you have a much better ion statistics compared to lower dwell times, but the overall signal does not increase, and that is the reason why dynamic MRM and also the triggered MRM is a very good and way to analyze the data, and you typically get very good RST values for the quantitation, and this is also what we could show in the validation study.